Today we're going to be talking about right triangle trig. You would have talked about this in geometry and then again in algebra 2. So most of this will be a review. Maybe some of this is a newer idea or newer topic, but hopefully most of it is review. So remember, when we have our trigonometry, most of our trigonometry, actually all of our trigonometry, is coming from triangles. And we always started with the right triangle. And we had our right triangle trig, and it created these functions for us. And hopefully you remember what they are, or at least you remember our acronym for them. So our main functions, our main three functions were our sine, cosine, and tangent. And we had that acronym of SOHCAHTOA to help us remember what those three functions were in relation to our side. So I write my acronym this way because I just always have. I've got the functions sine, cosine, and tangent, and then the a over h, the over h, and the o over a as ratios, because that's what they are. You've probably written it this way. Both are fine. I will probably fall into old habits and write it as the ratios just because that's how I do it. But they're the same thing. So there's SOHCAHTOA, and this is how we set up these trig functions, and it's all based off of where that angle is located. So I've got the angle theta down here in the bottom left-hand corner, and we've got these three sides of the triangle, and two of them are going to be named in relationship to that theta. We have the opposite side, which is what we would expect it to be. It's straight across. We have the adjacent leg, and then we have the hypotenuse as well. The hypotenuse is always that longest side. It's the one that's opposite the right angle. And then sine, cosine, and tangent are these ratios. So they're always going to be sine, cosine, or tangent of an angle value. And then sine of that particular angle value, so in this case theta, that's going to be equal to that opposite side over the hypotenuse. Cosine is equal to the adjacent side over the hypotenuse. And then tangent of theta, that's equal to the opposite side over the adjacent side. So that's how we get those O over H, A over H, and O over A for our acronym SOHCAHTOA. Again, I hope this is review. If it's not, I hope it makes sense. But these are functions of an angle. So we always, if we have sine, cosine, or tangent, we have to have the angle. I can't just say sine equals 1 over 2. It's sine of some particular angle. But these are all in right triangles. So when we're dealing with angle values like 120 degrees or 240 degrees, what we're going to try and do is create these right triangles when we draw in those angles. And we'll do that in a little bit. Now, those three functions aren't the only functions that we have. So we do have the sine, cosine, tangent functions. But we also have, and that's a little pushed together. We have our secant function, tangent, cosecant, and then cotangent. And so these functions, these are sometimes called the reciprocal functions because they're related to sine, cosine, and tangent as their reciprocals. So if I'm looking at my function sine, sine of an angle, or sine of theta, is going to be the same thing as 1 over cosecant theta, or I can write it the other way. That means cosecant theta equals 1 over sine theta. So these two here are reciprocals of each other. Then cosine and secant, those are reciprocals as well. So cosine of theta is equal to 1 over secant theta, or secant of theta is equal to 1 over cosine theta. And then our last one is our pairs of tangents, our tangent and our cotangent. So tangent of theta is equal to 1 over cotangent theta. Or we can rewrite that and say cotangent of theta has to be equal to 1 over tangent of theta. And so we can take those ratios that we have for sine, cosine, and tangent. And that means the reciprocals have to be the reciprocals of those ratios. So since sine is equal to the opposite side over the hypotenuse, that means cosecant of that angle is going to equal the hypotenuse over the opposite side. Cosine is the adjacent side over the hypotenuse. So that means because secant there is the reciprocal of cosine, that means secant is going to be the hypotenuse over the adjacent. And then the same thing happens here with the tangents. Since tangent of the angle is the opposite side over the adjacent side, that means cotangent is going to be the adjacent side over the opposite side. So we're going to use those ratios as well to help us, but you always want to go back to the reciprocal functions. Sine and cosecant are reciprocals, which means their ratios get flipped. Cosine and secant are reciprocals, cotangent and tangent are reciprocals. So again, here we have them. Sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite. So these are the reciprocal functions of each other. They flip upside down. Cosine and secant, tangent and cotangent. So using these, we're going to write our 6 trig values. So we want exact values. So we're not going to be doing any decimals. We're not going to do any approximations. We want exact values. And so here, we are going to want to know all 3 sides in order to set this up. So we do want to go through and figure out what this side is. And I don't actually know my angle value, so I'm not going to use sine, cosine, or tangent to do that. But what I do have is a right triangle. And so what I have here is a right triangle. And so right triangles always work for a squared plus b squared equals c squared, where c squared is that hypotenuse. So for us, that c squared, that c, the hypotenuse, is going to be 6. So we're going to use that to help us find the missing side first. So we can do that. We've got 2 squared plus x squared equals 6 squared, or 4 plus x squared equals 36. X squared equals 32. And because I want exact values, when I go to take the square root here, I do not want to use the calculator and get the decimal. I am going to take the square root of both sides, but what we need to do is we need to think back to algebra 1, algebra 2, and we want to simplify that square root. So there's a lot of different ways that you can do this. One common way is to build some people call it a tree or a factor chart, and look for pairs. If you have another way of doing this, go for it. If you think you have another way but you can't quite remember, come find me and we can talk through it. There's a lot of different ways to do this. What I like to do is I just build a factor chart. So I think of, okay, what divides evenly into 32? 4 and 8. 4 continues to break down into 2 and 2. 8 breaks down into 2 and 4. And then that last 4 can break down into 2 and 2. And what I'm looking for is I'm looking for pairs of 2s. So I have a pair of 2 down here. I have a pair of 2s here. They don't have to be off the same branch, but I do want to pair them up. And then I'm left with just this last 2 here that doesn't pair up with anything. So that's going to come in handy. That's going to come be important in just a second. But when I'm doing this, I'm looking for the pairs of 2s, and those are going to end up canceling with that square root. What happens is this x squared, I could rewrite that as 2 times 2 times 2 times 2 times 2. That's what 32 breaks into. 2 times 2 times 2 times 2 times 2. Or I could rewrite that as 2 squared times 2 squared times 2. So then when I take the square roots, square roots and squares cancel. That's the whole reason we take the square root, is to cancel with that square. And we get that x is equal to, well, it's going to cancel on that first 2 squared. It's going to cancel on the second 2 squared, but it doesn't cancel on the last one. So it stays underneath. And I don't have to do this middle step here, but what's happening is I'm looking at these pairs and I'm saying I've got 2 pairs of 2's. So those 2 pairs of 2's each get to send 1 2 outside of my square root. And then that last lone 2 doesn't have a pair, so that has to stay underneath. So that one stays down below. But at the very end, I get x is equal to 4 square roots of 2. Okay, so there's a lot of work in there. We haven't even talked about anything to do with trig, but there's a lot of work to get the exact side length there. So I get that this side length here is 4 square root of 2, and we're going to use that for our trig functions to come up with our 6 trig functions. All right, so we're going to start with the ones that we've been doing for a really long time. We're going to start with our sine, cosine, and tangent. We're going to have sine theta, and sine of an angle is equal to the opposite side divided by the hypotenuse. So if I look at my angle theta, the side opposite theta is 2. This hypotenuse is 6, so that means sine of theta is equal to 2 over 6. And we typically like to reduce that. 2 over 6 reduces to be 1/3. So sine of theta is 1/3, and that's an exact value. Okay, we can go and we can do cosine. Cosine of theta, if you think back to your acronym, so COTOA, cosine is adjacent over hypotenuse, and we just figured out that adjacent is 4 root 2. That's an exact value, so I get that it's 4 root 2 over 6. And again, I want to simplify it, and so I can't simplify numbers under a square root with whole numbers, but I can simplify the 4 and the 6. And that's going to simplify to be 2/3. So this becomes 2 root 2 over 3. And that's my cosine value. And then my last one here of the 3 initial ones before we get to our reciprocal functions is the tangent of theta. And tangent of theta, that's TOA, is opposite over adjacent. And so here I get my opposite side is 2. My adjacent side is 4 root 2. And we have to simplify this for a couple different reasons. First of all, those coefficients of 2 and 4, those reduce. So we want to simplify that anyways. But then we also need to simplify it because we have that square root of 2 in the denominator. And so this is not what we would consider rationalized. We want to make sure that that root 2 comes out of the denominator. And so we're going to do that, but I do want to first, and it's almost always better if you first simplify those 2 values. Okay, if we reduce those, if anything, it just gives us smaller numbers to work with. So the 2 over 4, that would reduce to 1 over 2. So this becomes 1 over 2 root 2. And now I want to deal with that square root of 2 in the denominator. So we're going to rationalize it. We're going to multiply by a form of 1. So we're going to multiply both the top and the bottom by the square root of 2. And so what we get is just root 2 in the numerator. We have that initial 2. And then we have these 2 root 2. So root 2 times root 2 gives me a 2. So I can just do a little bit more cleanup. I've got 2 times 2 in the denominator. I get that tangent of theta is the square root of 2 divided by 4. And that would be my final exact answer. So quizzes and tests, I'm going to expect you to be able to rationalize it. If you want more practice with that, that's fine. Come find me and we can do a bunch of practice with that. But final exact values for trig functions are going to be reduced fractions and no square roots in the denominator. In the numerator is fine, but in the denominator, no. All right. For our reciprocal functions, we're going to start with cosecant because cosecant is the reciprocal of sine. So this is the same thing as doing like 1 over sine, or in our case, that's going to be the hypotenuse over opposite. Okay, so sine is opposite over hypotenuse. So cosecant cosecant is hypotenuse over opposite. So this is going to say, okay, our hypotenuse was 6, our opposite was 2, and I just want to reduce that. When I reduce that, I get 3, which, if you look up here, that's the same thing as taking that reduced 1/3 and simplifying and doing the reciprocal of that, getting 3 over 1. 3 over 1 and 3 are the same. So you have two different options. Once you've written out sine, cosine, and tangent, for cosecant, secant, and cotangent for the reciprocal functions, you can go through the hypotenuse over opposite, hypotenuse over adjacent, adjacent over opposite. Or you can take the 3 values from up above and do their reciprocals. Now, when you do that, there is some tricks to help with the algebra cleanup at the end, which we'll talk about when we get to that cosine and that tangent. But we're going to go through, we're going to do our last two here. We have our secant. Secant is the reciprocal of cosine, so I could take that value we have for cosine of 2 root 2 over 3, and I can flip that upside down. So that's what we're going to do here because it's already been reduced for us. So I get 3 over 2 root 2. Now if I wanted to, I could do this as the adjacent over the hypotenuse, which would have started off with, secant is the hypotenuse over the adjacent. So we could have started with 6 over 4 root 2, but then we would have reduced the 6 and the 4 to give us 3 over 2 root 2. But I do want to simplify this. I do need to rationalize it. So I'm going to multiply by root 2 and root 2 for both top and bottom. And then I'm multiplying across. I get a 3 root 2 in the numerator. And then a 2 times 2, because that root 2 times root 2 gave me that extra 2 at the end. And just do a little bit of cleanup. So I get 3 root 2 over 4. Very last one here, tangent. I can go through and I can do this process of cotangent of my angle theta is I could take that root 2 over 4 from tangent up above, and I could make that 4 over root 2, but then I would have to go through that process of rationalizing again. In this problem, for cotangent of theta, I think it is easier to take the reciprocal ratio of the adjacent over the opposite and do this. Because if I do this right here, if I think about the adjacent side, that was that 4 root 2. And the opposite side was 2. And I already have it rationalized. I've already gotten the square root of 2 out of my denominator. So all I need to do is do a little cleanup with that 4 and the 2, and it just creates this new nice 2 root 2. So you have a couple options. You could do the 4 divided by the square root of 2 and then rationalize that. Will work for you. It'll get you the same thing at the end. Or you can go back to the pattern and say, okay, well, if tangent is opposite over adjacent, then cotangent is adjacent over opposite. Okay? So those are our exact values for our 6 trig functions. In number 2 here, we're going to sketch a right triangle. We're going to draw the picture first, and then we are going to determine, okay, we know sine of theta is 5 over 13. I want to know what my 5 other trig functions, what cosine, tangent, secant, cosecant, and cotangent are. So we are going to start by drawing this triangle here. So it is going to be a right triangle. These are all going to be right triangles. And I'm going to draw them on my XY plane just because that's how we've been drawing angles the last couple of days. You can just draw a triangle out by itself. I tend to like this a little bit better. It is positive sine, so we're going to stay in the first quadrant. We don't have to stay in the first quadrant. Sine is positive in the first and second. We're going to stay in the first quadrant because the way we set this up, sine is going to stay in that first quadrant. We'll talk about more of that later. Well, my angle value is down here like we graphed it the other day. And I want to think about what sine is. Remember, sine of theta, sine of an angle, is the opposite side over the hypotenuse. So that means on this triangle here, opposite of theta is going to be 5, and the hypotenuse is 13. So just like before, I need to go and I need to figure out what that adjacent side is. So we're going to do our Pythagorean theorem. I'm going to do 5 squared plus x squared equals 13 squared. And if you go through and you square it all out, you should get that x is equal to 12. A little bit nicer this time. We don't have a square root. We have a nice whole number. It gives a Pythagorean triple. That's what those are called when all three numbers are whole numbers. We get 12 there. And then I can go through and I can do my 5 other trig functions. I have all the pieces of my triangle. So I can start with cosine of theta, which is adjacent over hypotenuse. So this would be 12 over 13. And that doesn't reduce, so I don't have square roots, so I don't have to worry about rationalizing it. And I can go and I can do, okay, well, tangent of theta, that's going to be the opposite, 5 over the newly found adjacent 12. You can go and say, okay, well, now I can do cosecant of theta. That's the reciprocal of sine. So I can say, okay, this is the hypotenuse over the opposite, or I can look at this 5 over 13 and just flip that and get 13 over 5. I don't have to worry about rationalizing because there's no square roots here, so I can just flip my fractions, and then I can say, okay, same thing, secant of theta, that's going to be cosine flipped, so that's 13 over 12. And then cotangent of theta, that's the reciprocal of tangent, so I'm going to flip and get 12 over 5. All right, so writing the sine, cosine, tangent, cosecant, secant, cotangent, this time was a little bit faster because we didn't have to do simplifying. We didn't have to do any rationalizing. It took a little bit more work because we weren't given the triangle, so we did need to draw that. It's almost always going to be better for you if you draw a picture. And we did need to do the Pythagorean theorem. But again, it was a little bit nicer because we didn't have to simplify. We got a nice whole number with that Pythagorean theorem. We do have these special right triangles. So the other day in class we talked about why 45 or pi over 4 was an important value. And then we're also going to talk about the pi over 6 and the pi over 3 or the 30 and 60 degrees and why these are important values. It's because of these special right triangles. They have these patterns that the side lengths always follow, no matter how big or how small it is. So this is sometimes called a 1, 1 square root of 2 triangle because the side lengths are 1, 1, and the square root of 2. Sometimes it's called an isosceles right triangle. Most of the time, though, we're going to call it 45, 45, 90. Okay, we're going to name it by its angle values. And it has this pattern, though. These legs here are always going to match every single time. If they're 45-degree angles, then the legs are going to match. So if this leg down here is 5, then this leg is 5. And then the hypotenuse is always the leg length times the square root of 2. So if my legs are 5, then the hypotenuse is now going to be 5 root 2. And it works for any of those leg lengths. So if I have a 45, 45, 90 triangle here, and I say my leg is, 17.2, and then the other leg has to be 17.2, I could go through and do a squared plus b squared equals c squared, but this is also 17.2 times the square root of 2. Every single time to get from the leg to the hypotenuse, you multiply by the square root of 2. There's also the 30, 60, 90 triangle, and this pattern isn't quite as simple or as easy to remember because the leg lengths this time are 2 different sides. And the reason why is because the angles are different. So we have a 30-degree angle and a 60-degree angle. In radians, that would be pi over 6 and then pi over 3. And these are going to have their own patterns as well. So I always talk about them in relationship, the sides opposite the angles. So this 30-degree angle or pi over 6 is opposite what's the short leg. the 1. And then that 60-degree angle, that's opposite the long leg. It's not the longest side, but it's the longest leg. And then at the end, we have our hypotenuse as well. The hypotenuse, again, is always across from that 90-degree angle. And so the pattern here is a 1 square root of 3, 2 pattern. And again, this follows no matter what that short leg starts off to be. That short leg, the one across from the 30 degrees, if that is, say, 5, then my hypotenuse is going to be 2 times 5, or more commonly called 10. And my long leg, the one across from the 60, is going to be 5 root 3. Okay, and so just like with the 45, 45, 90, this works for any leg length, any short leg length. So I can redraw it and I can flip it around, but it's always based off of the sides across from their angles. So across from the 30, and we're going to actually redraw that so it looks a little bit more, makes a little bit more sense for the picture. My 30 degrees is up at the top, and the bottom leg is the one across from the 30. If this is 21.6, then my leg across from the 60 is going to be 21.6 root 3. And then my hypotenuse is going to be 21.6 times 2, which is 43.2. Okay, so every single 30, 60, 90 triangle follows this pattern. If I don't know the angles, then I can't use the pattern. Or if my angles are anything other than 30, 60, and 90, I can't use the pattern. But if I know these are my angle values in either degrees or radians, and I know that these are this special right triangle, then I can use this pattern to save time in Pythagorean theorem to find my missing side lengths. So you have a note sheet, you have a little box, hopefully you have your note sheet with you, and you have that little box. Try and fill in that answer key, or try and fill it in. You want to use those special right triangles. I would use the original triangle, the one with the, for 45, 45, 90, the 1 square root of 2, because then we won't have to do any reducing. We might have to do some rationalizing, but we won't have to do any reducing. And then for the 30, 60, 90, use that, this one here, the 1, 2 square root of 3, because again, you won't have to do any reducing. Maybe some rationalizing, but no reducing. So take a minute. I'll put it up in a second so you can check your work. Take a minute, try and fill in that box on your own. All right, hopefully you were able to get these. Sine of 30, that's the same thing as sine of pi over 6, because 30 degrees and pi over 6 radians is the same. That's going to be 1/2. Cosine of 30, it's going to be root 3 over 2, and then tangent of 30, that's would have started off as 1 over the square root of 3, and then we would have rationalized it. So this would have been 1 over the square root of 3. And then to rationalize it, we would have multiplied top and bottom by square root of 3 over square root of 3, and that gave us this root 3 over 3. So if you have 1 over the square root of 3, you're on the right track, but you do want to continue on that path to rationalizing it. All right, so sine of 45 and cosine of 45, those also needed to be rationalized. They would have started off as 1 over the square root of 2. And then sine of 60, that would have, sine of 60 was fine. Sine of 45 and cosine of 45, those need to be rationalized. But the rest should have been fine when you put them in their ratios of opposite over adjacent, or opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, that we got these values. All right. Hopefully this is somewhat familiar from last year, and maybe even from geometry a little bit. Of getting these exact values. So these are ones that you're going to want to know. We're going to use them a bunch, and hopefully they'll start coming back to you if you did them. Hopefully you're starting to remember some of these. So using that chart, using that table, we want to try and fill in these things right here. And so right now we have a secant function. And I know the ratio is 2 over the square root of 3. What I'm trying to figure out is my angle value. And we do have some restrictions. We have some constraints on our angles. Our angles are going to be between 0 and 90 degrees or 0 and pi over 2. And so the way I do this is I do like to graph these. I do like to draw these as a triangle because that's where all of these are coming from. They come from these triangles. So I can draw this, and I'm going to be in the 0 to 90 degree range, or 0 to pi over 2. That is going to keep me in that first quadrant. That's very helpful. So I can draw in a triangle. I don't know what the angle value is, so I'm just going to draw in a line and hope that it's close and not worry about that too much, but I do want to be in that first quadrant. And I want to fill in my side lengths here. So I want to think about secant. And secant is connected to cosine. Secant is the reciprocal of cosine. So since cosine is adjacent over hypotenuse, secant is going to be hypotenuse over adjacent. So that means my value of 2 over root 3, that tells me that 2 is my hypotenuse and root 3 is the adjacent to the angle. So if I mark my little angle in here, my hypotenuse I can label as 2, and my adjacent side I can label as root 3. And those two values are two values from our special 30, 60, 90 triangle. The only side that is missing is the shorter leg of 1. And if you forget it, you can do Pythagorean theorem. You can do root 3 squared plus y squared equals 2 squared. And 2 has to be the one by itself because that's the hypotenuse. And I'm actually calling this missing side here y because it's a vertical length, and y's tend to go with vertical lengths and x's go with the horizontal. So since it's a vertical length that's missing, I do call it y. If you call it x, that's not a big deal. But you don't even need to do Pythagorean theorem. If you recognize that the 2 as the hypotenuse and the root 3 of a leg come from a special right triangle, you could hopefully remember that that third side has to be a 1. And then we just need to figure out, or we're trying to remember, across from the 1 is what angle value? 1 is smaller than root 3. Root 3 is, I think, 1.5 something. I'm not quite sure. But 1 is smaller than that. And so it needs to be across from the angle, the smaller of the two angles. So 90 I know is down in that bottom right corner. So my options are between 30 and 60. So that means this angle here needs to be 30 degrees. So my angle value in degrees is going to be 30. And then to get to radians, I just want to convert, or hopefully after a certain point, you'll remember that 30 degrees is pi over 6 radians. Okay? So it kind of looks like a lot of work, but this is really the process you want to go through. When we're getting to being in different quadrants or in slightly more difficult ratios, this process is going to be much more helpful. So right now it looks a little more, maybe it looks more complicated than it needs to be, but it's this process when we get to more difficult problems is going to be beneficial and much more helpful for us. All right, I want you to try this one on your own. Same process, start off with sine. We've got those same restrictions in terms of our, angle values, needing between 0 and 90 degrees or 0 and pi over 2. So again, that means we're going to be in that first quadrant. But go ahead, you can pause the video, try this one on your own, and then come back and check with what I have. All right, so we actually end up with the exact same triangle again. So we end up with the same angle value. So the reason the function value is different is because it's a different function. This time we had sine instead of having secant. But we do end up with the same triangle and the same angle values. So hopefully you saw that pattern again with the 1, 2, and then that missing side would be the square root of 3. And our angle value, the one that's the vertex, is at the origin. It's across from the 1. It's across from the shorter leg. So that's our 30-degree angle. All right, go ahead and do cosecant, and then you can pause the video, try and draw it, and then come back and check with me. All right, third one in a row where we have the exact same triangle, exact same angle value. This one is a little bit trickier because that function value started off as just 2. So it's you have to remember that any integer is actually a ratio. You can throw it over 1. So cosecant is 1 over sine. It's the reciprocal of sine. So sine is opposite over hypotenuse. So cosecant is hypotenuse over opposite. So that function value of 2, or 2 over 1, tells me that the hypotenuse is 2, the opposite side is 1, and again we have that same 30, 60, 90 triangle we're looking at the angle across from the 1, so again it's 30 degrees, or pi over 6. Alright, we're going to use our calculator on these ones. You do want to be careful when you're calculating these with a calculator that you have the correct mode. Your calculator, depending on when you last use it for trig functions, could be in radian mode, it could be in degree mode. So you want to make sure that you go back and forth between them, that you are able to go back and forth between them, and that you do have the correct mode depending on what sort of angle value we have. So just a quick reminder, you can click the mode button, and then it's the third line down. You either want radians or degrees highlighted. For this particular problem, we want degrees highlighted. And then you can exit out of that screen, and you just hit cosine 28, and you should get this beautiful ratio of 0.88, and this would round to 3. It was 0.8829. I mean, right, 0.883. We do want to, when we're using our calculator, typically to have at least 3 decimal places. That's usually a good value, a good number of decimal places to have. So at least 3. These on the calculator should hopefully take you about maybe 5 seconds, maybe 10 if you have to check your mode. Make sure your mode is in the correct number, the correct form. But really these should be fairly straightforward if you have your calculator. Go ahead and you can do secant of 28. This one's going to be a little bit harder. You want to think about, okay, secant is not on your calculator. So what is secant related to? Which original function is it related to? Secant is the same thing as 1 over cosine. So this right here is 1 over cosine of 28. So putting in your calculator, this one is going to take you a little bit longer, maybe 10 seconds, 15 seconds. But you're going to type in 1 divided by cosine 28. And this time we should get 1.13. It was 25, so that would round to 3. 1.133. All right, these next 3 problems we're going to do without a calculator. So we want to treat them like we did the ones before. We have our ratios. We have our trig function. So we want to draw the triangle. All of these, again, are going to be in that first quadrant. We want to think through what those different ratios are, what those different functions are. So for that cotangent function, cotangent is the opposite or the reciprocal of tangent. So tangent is opposite over adjacent. So cotangent is going to be adjacent over opposite. And again, that ratio is just 1. And so if I want to, and we want to do this, we want to make that 1 into a 1 over 1. So for my angle value here, my opposite side and my adjacent side are both 1. And so hopefully we realize that that is the 1, 1 square root of 2 triangle, or that 45, 45, 90 triangle. And we get that our angle value, or theta, is 45 degrees, which is our pi over 4 radians. All right, so go ahead, do the next 2, secant of theta, cosecant of theta. Remember that secant is the reciprocal of cosine. Cosecant is the reciprocal of sine. All right, so for secant of theta equals the square root of 2. Secant, remember, is that 1 over cosine, so it's going to be hypotenuse over adjacent, and we can rewrite the square root of 2 as the square root of 2 over 1. So drawing that triangle, again, we're in that first quadrant. Our hypotenuse is going to be the square root of 2, and our adjacent leg is 1. So again, we have that 1, 1 square root of 2, or the 45, 45, 90 triangle. So our angle theta, again, is 45 degrees, or pi over 4. That last one, cosecant theta, is 2 root 3 over 3. This one is probably the trickiest of them all, because if you were to draw that triangle exactly as the ratio tells us, so you've got that cosecant is 1 over sine, so it's going to be hypotenuse over opposite. If I draw it in this, to start off with it, I just have a 2 root 3 as my hypotenuse and a 3 as my opposite side. Ooh, I just realized I did this wrong. That root 3 should be down here, so we'll fix that. We'll just do this all together. I do have a slight issue here. So that 2 root 3 and 3, those don't come from one of our special right triangles, or at least they don't come obviously from one of those special right triangles. And so what I would recommend doing is, if you notice that that numerator is a square root of 3 in it, and the denominator has a 3, whenever you have that pattern, so if we had like a square root of 2 over 2, or the square root of 5 over 5, or in this case a square root of 3 over 3, that meant we started off with a square root of 3 in our denominator, and we rationalized it, we multiplied by root 3 over 3 to get it out of the denominator into the numerator. So we can unrationalize this, and we can get this as a 2 over the square root of 3. This is the same thing as if we were to once again multiply top and bottom by root 3 over root 3. And then this rewrites it as 2 over the square root of 3, which is a little bit more helpful, because then when I go and put these values in, my hypotenuse is just 2, and my opposite side is just the square root of 3, and those come from that special right triangle where we have, now my adjacent side has to be 1. So across from the 1, that's my 30-degree angle, so the angle I care about is actually this 60-degree angle down here. So my theta is going to be 60 degrees, or pi over 3 radians. Okay. So that unrationalizing, that's sort of the trickiest part, and if you have questions on that, just come find me and we can talk through that some more together. Last thing we're going to talk about is just quick reminders of things from geometry, some terminology. So we have angles of elevation, angles of depression, and this is going to lead us into some word problems where we use our trig functions to find missing sides. And so both of these are always built off of a horizontal line. So angles of elevation open up, those are like our positive angle values. And then angles of depression open down, those are going to be like those negative angle values that they have. But they always come from that horizontal line. So we're going to use these sometimes in our word problems. What we're going to do is we're going to use our SOHCAHTOA and then our reciprocal functions of cosecant, secant, and cotangent to find missing side lengths. We're going to use our calculators here to help us. So number 9 here, we have the surveyor is standing 115 feet from the base of the Washington Monument. So that's this horizontal distance down here. What's that horizontal distance? You can't see that green color. That's better. That's our horizontal distance. And we have that the angle of elevation, so that's the angle down at that surveyor, is 78.3 degrees. And we want to know how tall that Washington Monument is. So we're trying to figure out the vertical distance. So we use the y variable. If you used x, that's okay, but typically for those vertical distances, we like the y variable. So what we want to do is we want to set up a trig function. So we're going to go back to our best friend SOHCAHTOA to help us first determine which trig function we want to use. Do I want to use sine, cosine, or tangent? So again, this is always built off of that angle. So for that location of that 78.3 degrees, we're going to look and say, okay, well that 115, that horizontal distance, that is the adjacent leg. And we're looking for that vertical distance, y, which is our opposite leg. And so if I think through sine, cosine, and tangent, the one that uses opposite and adjacent, That's going to be our tangent function. So I can set this up. I can say tangent of my angle value, 78.3 degrees, is going to be equal to the opposite side y divided by the adjacent side of 115. And so we just want to solve this for y. And the way I do this in my geometry classes is I always put this over 1, and then we can do our cross multiplication. We can multiply across that equal sign. So in this particular problem, we would get 1 times y, or just y, is equal to 115 times tangent of 78.3. Then we go to our calculator. And we do want to make sure that we're in this correct mode, that we're in degree mode. We should be, since we did some problems earlier in degree mode. But we just go to our calculator, type in 115, tangent of 78.3, and we should get 555.31. We'll round to the nearest hundredths, 2 decimal places. And this is in feet. So it's about 555.31 feet tall. All right. Most of the time when we're doing these word problems, our angle values will be in degree measurement. Very rarely will we have one in radians, but we're going to be doing other problems where we're going to be in radians, so you always want to make sure you're being careful about what mode you're in. If you get a number that does not make sense, if you get a length, like a height that's negative, then that should be some sort of clue that we're probably in the wrong mode. Most of the time if we have an issue, it's just your calculator's in the wrong mode. All right, this last problem, we're trying to figure out first what the length of C is, and then what the length of A is. So C is that length of the skateboard, that hypotenuse distance, and then we're going to try and find that horizontal length. So we're going to have to set up 2 different trig functions here. So that first one, to find C, again, we're going to build off of that angle. We've got an angle of about 18.4 degrees. Okay. So again, hopefully this is somewhat review for us, nothing brand new. Hopefully it's starting to come back to you. So we're using sine, cosine, tangent, reintroduce the reciprocal functions, cosecant, secant, cotangent, and then we reintroduce those special right triangles as well.